Let yourself settle into this moment. Feel the surface beneath you supporting your weight, taking the burden from your muscles and bones. Take a slow, deep breath, drawing air into your lungs and feeling your chest expand. As you release that breath, imagine releasing the tension of the day with it, letting it drift away like mist evaporating in morning sunlight. Tonight, we're going to explore something extraordinary, something that exists at the very edge of what's physically possible in our universe. But you don't need to work at understanding, don't need to memorize or strain to remember. Just let the words wash over you, painting pictures in your mind of cosmic wonders so extreme they challenge everything we think we know about reality itself. We're going to meet a cosmic monster tonight, but it's not the one you might expect. It's not a black hole, though it's just as strange and just as powerful in its own way. This is something that bends the laws of physics in directions we're only beginning to understand. So close your eyes if you'd like, or let them rest on some distant point, and drift with me into the depths of space where the strongest magnets in the universe wait to tell their story. This cosmic monster breaks every rule, and it's not a black hole. When astronomers talk about cosmic monsters, your mind probably jumps immediately to black holes. Those gravitational behemoths that devour everything, even light itself, certainly earn their fearsome reputation. But tonight, I want to introduce you to something equally monstrous, equally impossible by the standards of everyday experience, yet fundamentally different. These objects don't hide behind event horizons. They don't cloak their secrets in impenetrable darkness. Instead, they broadcast their existence across the cosmos in bursts of energy so powerful they can be detected from billions of light years away. I'm talking about Magnetars. And to understand why they're so remarkable, we need to start with a simple question. What makes a magnet powerful? You've probably held a refrigerator magnet in your hand at some point. Maybe you've played with the stronger neodymium magnets, the ones powerful enough to pinch your fingers if you're not careful. Those rare earth magnets, among the strongest we can manufacture, have magnetic fields measuring about 1.25 Tesla. That's impressive by human standards. It's strong enough to slightly distort the atoms in their vicinity, strong enough to erase the magnetic stripe on a credit card if you hold it close enough. Earth itself is a magnet, though a relatively weak one. Our planet's magnetic field, generated by the churning motion of molten iron and nickel in the outer core, measures somewhere between 30 and 60 microteslas at the surface. That's less than 1/10,000th the strength of a refrigerator magnet. Yet this weak field is enough to deflect the solar wind, protecting our atmosphere from being stripped away. It's enough to turn compass needles and create the shimmering auroras that dance across polar skies. Now, hold those numbers in your mind, because we're about to leave them so far behind that they become essentially meaningless. A magnetar's magnetic field measures somewhere between 10 and 100 billion Tesla. Let me put that another way. A magnetar's magnetic field is trillions of times stronger than any magnet we've ever created on Earth. It's billions of times stronger than the magnetic fields around ordinary neutron stars, which are themselves unimaginably powerful by terrestrial standards. Numbers like these are difficult to grasp in any visceral way. Our brains didn't evolve to comprehend magnetic fields measured in the trillions, but let me try to give you some sense of what a magnetic field this powerful actually means. If you were to float within about 600 miles of a magnetar, something would happen to you that has never happened to anyone or anything in human history. The atoms that make up your body, the hydrogen and carbon and oxygen and nitrogen that form your bones and blood and brain, would begin to deform. Atoms, as you might remember from high school chemistry, are mostly empty space. A tiny nucleus sits at the center, and electrons orbit around it in fuzzy probability clouds. The shapes of those electron clouds, determined by quantum mechanics, define how atoms bond together, how chemistry works, how biology functions. But in a magnetic field as powerful as a magnetar's, those delicate electron clouds would be squeezed and stretched like putty. Instead of their normal spherical or dumbbell shapes, atoms would be forced into long, thin cylinders, stretched along the magnetic field lines like iron filings aligning themselves around a bar magnet. A hydrogen atom, normally about 1/10 billionth of a meter across, would become more than 200 times narrower in the direction perpendicular to the magnetic field. This isn't just a minor distortion. This is a complete reconstruction of atomic structure, a fundamental alteration of the shapes that allow chemistry to function. The biochemistry that keeps you alive, that allows your cells to metabolize energy and your neurons to fire, would simply stop working. Life as we know it cannot exist in such conditions, and that's at a distance of 600 miles. At closer ranges, things get even stranger. The magnetic field around a magnetar is so powerful that it affects not just matter, but the very fabric of empty space itself. Quantum field theory tells us that what we think of as empty vacuum is actually seething with virtual particles, electron-positron pairs, that blink into existence for the briefest of moments before annihilating each other. These quantum fluctuations are a fundamental feature of reality, predicted by the equations and confirmed by countless experiments. In the presence of a magnetar's field, this quantum foam behaves differently. The vacuum itself becomes polarized, split into different components, the way light passing through certain crystals gets split into separate beams. Empty space near a magnetar acts like a crystal, bending and separating light in ways that don't occur anywhere else in the cosmos. This phenomenon, called vacuum birefringence, had been predicted by theory for decades, but it wasn't until observations of magnetars that astronomers found direct evidence of it actually happening. X-ray photons traveling through this magnetized vacuum don't just pass straight through. They can split into two separate photons, or two photons can merge into one. Light itself behaves in ways that seem impossible by the standards of our everyday experience, following rules that only emerge at these extreme field strengths. And remember, all of this weirdness, all of these reality-bending effects is happening around an object that's only about 12 miles across. A magnetar is roughly the size of Manhattan, a city-sized sphere floating in space, yet its influence extends for thousands of miles in every direction, warping space-time and quantum fields and the very definition of what it means for space to be empty. But here's the truly remarkable thing about magnetars. They're not theoretical constructs. They're not mathematical fantasies dreamed up to test the limits of physics equations. They're real. They exist. And sometimes they let us know they're there in the most dramatic way possible. The discovery that changed everything. The story of how we discovered magnetars begins, appropriately enough, in the Cold War. It's March of 1979, and the Soviet Union has two unmanned space probes, Venera 11 and Venera 12, drifting through space after successfully dropping landers onto Venus a few months earlier. The probes are equipped with instruments designed to detect gamma rays, the highest energy form of light, radiation so energetic that each photon carries more energy than an entire visible light photon, by factors of millions or billions. The spacecraft are sitting relatively quietly, monitoring the background radiation of space, when suddenly, at 10:51 in the morning Eastern Time, they're hit by an absolute storm of gamma rays. The detectors, designed to pick up faint cosmic signals, are completely overwhelmed. The burst is so bright, so intense, that it actually saturates the instruments, flooding them with more photons than they were ever designed to handle. But the Soviet probes aren't the only ones to detect it. Satellites orbiting Earth pick up the signal. Deep space probes belonging to NASA register the burst. Over the next few seconds, a wave of gamma radiation sweeps through the solar system, detected by spacecraft spanning millions of miles. By carefully comparing the arrival times at different detectors, astronomers can triangulate the source to a specific patch of sky in the southern hemisphere, in the constellation Doradus. The burst lasts only about 1/5 of a second at its peak. But in that brief flash, something released more energy than the sun produces in 1,000 years. The source, whatever it was, lay far outside our solar system. Somewhere in the large Magellanic Cloud, a satellite galaxy orbiting the Milky Way about 160,000 light-years away. Even at that enormous distance, the burst was bright enough to measurably disturb Earth's ionosphere, the layer of charged particles high in our atmosphere that reflects radio waves. Astronomers had never seen anything quite like it. They cataloged the event as a gamma-ray burst, GRB 790305b, and began the long process of trying to figure out what could possibly produce such an explosion. Over the next 2 decades, similar bursts were detected, though most were far more distant, occurring in other galaxies billions of light-years away. But a handful came from much closer sources, objects within our own galaxy. These nearby sources showed a peculiar characteristic, they repeated. Unlike the distant gamma-ray bursts, which seemed to be one-time events marking the deaths of massive stars, these nearby sources would flare up again and again, sometimes years apart, sometimes with just months or weeks between outbursts. Astronomers called them soft gamma repeaters, or SGRs, because while they did emit gamma rays, most of their energy came out at lower, softer energies compared to the classic distant bursts. The mystery deepened in 1998 when another powerful burst hit Earth, this time from an object designated SGR 1900+14. Then, on December 27, 2004, came an event that would help astronomers finally piece together what was happening. It was just after 2 o'clock in the afternoon, Universal Time, when the gamma rays arrived. The initial spike was so bright, so powerful, that it overwhelmed virtually every gamma-ray detector in orbit. For the first 0.2 of a second, the source poured out more energy than the sun will produce in 250,000 years. After that initial flash, the emission continued at a lower level for more than 5 minutes, gradually fading. The source was SGR 180620, an object located about 50,000 light-years away on the far side of the Milky Way in the direction of the constellation Sagittarius. Even at that distance, the burst was bright enough to temporarily expand and ionize Earth's upper atmosphere. Radio communications were disrupted. Satellites went briefly offline, their systems overwhelmed by the sudden flood of high-energy particles. For a brief moment, this distant object had reached across 50,000 light-years of space and actually affected our planet's environment. If that same burst had occurred from a source just 10 light-years away, about twice the distance to the nearest star system, it would have been devastating. The gamma radiation would have stripped away much of Earth's ozone layer, exposing the surface to harsh ultraviolet light from the sun. The effects would have been similar to what might happen if a 12-kilota nuclear bomb detonated at an altitude of about 4.5 miles. Mass extinction would likely have followed. But what kind of object could produce such an incredible release of energy? What cosmic engine could pour out more power in a fraction of a second than our entire sun generates in hundreds of thousands of years? The answer, physicists gradually realized, was a magnetar. And to understand how they produce these titanic bursts, we need to understand how magnetars form in the first place. Birth of a monster. The story of every magnetar begins with a massive star, a sun many times larger and more luminous than our own. Picture a star weighing somewhere between 10 and 25 times the mass of our sun, burning through its nuclear fuel at a prodigious rate. Where our sun will shine steadily for 10 billion years, these massive stars live fast and die young, exhausting their fuel in just a few million years. For most of its life, such a star generates energy through nuclear fusion, converting hydrogen into helium in its core. The heat and pressure from this fusion creates an outward push that balances the inward pull of gravity, keeping the star stable. But eventually, the hydrogen in the core runs out. The core contracts and heats up, becoming hot enough to fuse helium into carbon and oxygen. Around this core, hydrogen continues fusing in a shell, and the star swells into a giant. As the helium depletes, the process continues. Carbon fuses into neon and magnesium. Neon fuses into oxygen. Oxygen fuses into silicon. Each stage happens faster than the last because each generates less energy per fusion reaction, forcing the core to burn hotter and faster to maintain the pressure that keeps the star from collapsing. Silicon fusion lasts perhaps a day before producing iron, and here the chain stops. Iron cannot be fused to release energy. Fusing iron requires energy input rather than producing it. The star has reached the end of the line. The result is an onion-like structure with shells of different elements surrounding an iron core. The core sits there, growing larger as silicon continues fusing in the shell around it, but producing no energy of its own. It's held up only by quantum pressure, the same weird effect that keeps electrons in an atom from all occupying the same state. But there's a limit to how much mass quantum pressure can support. When the iron core reaches about 1.5 times the mass of the sun, quantum pressure can no longer hold it up against gravity's pull. The core collapses. What happens next occurs so fast that it's almost impossible to comprehend. The core, roughly the size of Earth, collapses inward at speeds approaching 1/4 the speed of light. In less than 1 second, it shrinks from something Earth-sized to something about 12 miles across. The density rises to levels where atomic nuclei are literally touching, packed together like oranges in a crate, and then beyond, into densities where the distinction between individual nuclei starts to blur. The outer layers of the star, no longer supported by the pressure from the core, begin to fall inward, accelerating as they go. But when they hit the now super-dense core, they encounter something as hard as a surface can possibly be. The collision between the infalling matter and the incompressible core creates a shock wave that propagates outward through the star. The star explodes, blasting its outer layers into space in what we observe as a supernova. But the core remains. What's left is a neutron star, a sphere about 12 miles in diameter, containing somewhere between 1.5 and 2 times the mass of our sun. It's made almost entirely of neutrons, those electrically neutral particles normally found only inside atomic nuclei. The density is so extreme that a teaspoon of neutron star material would weigh more than 100 million tons on Earth. Now, here's where magnetars diverge from ordinary neutron stars. The key, researchers believe, lies in rotation. During the collapse, the core spins up dramatically. This is simple conservation of angular momentum, the same physics that causes figure skaters to spin faster when they pull their arms in. A stellar core the size of Earth, rotating perhaps once every few days, collapses to something 12 miles across. By the time it finishes contracting, it might be spinning hundreds of times per second, completing rotations faster than a hummingbird's wing beat. In the incredibly hot, dense environment of a newly formed neutron star, this rapid rotation, combined with convective currents in the still settling interior, can drive what's called a dynamo effect. Charged particles moving in the star's interior generate electric currents, and those currents create magnetic fields. The magnetic fields, in turn, affect the motion of the charged particles, creating a feedback loop. Under the right conditions, this dynamo can amplify the star's magnetic field to incredible levels. Computer simulations show that this process happens very quickly, in the first few seconds after the neutron star forms. As the interior churns and convects, driven by the tremendous heat and the rapid rotation, the magnetic field grows exponentially. Within perhaps 30 or 40 seconds, the field can reach the extraordinary values we observe in magnetars, 10 to the 14th up to 10 to the 15th Gauss, 1,000 times stronger than the already intense fields around ordinary neutron stars. But not every neutron star becomes a magnetar. The process requires specific conditions. The core needs to be rotating fast enough to drive the dynamo efficiently. If it's spinning too slowly, the amplification never gets going. If it's spinning too fast, the centrifugal forces might tear the star apart before it settles into a stable state. Recent research suggests that many magnetars may form through a different route via binary star systems. Imagine two massive stars orbiting each other, locked in a gravitational dance. As one of them swells into a giant near the end of its life, its outer layers can overflow onto its companion. This mass transfer spins up the companion star, setting it rotating faster and faster. Later, when the companion star reaches the end of its own life and collapses to form a neutron star, it's already spinning rapidly from that earlier mass transfer. This pre-collapse rotation gives the dynamo mechanism a head start, making it more likely that the resulting neutron star will develop the ultra-strong magnetic fields characteristic of magnetars. In 2230, astronomers announced the discovery of a star called HD 45166, located about 3,000 light-years from Earth. This star has the strongest magnetic field ever measured in a massive star, about 43,000 Gauss, far stronger than any similar star should have. The star is actually part of a binary system, and it appears to be following exactly the evolutionary path that should lead to a magnetar. In a few million years, when HD 45166's companion star finally dies and collapses, astronomers expect it will form a brand new magnetar, providing the first opportunity to observe this process from beginning to end. But once a magnetar forms, what does it actually look like inside? What's going on in this city-sized sphere of supercompressed matter with its reality-warping magnetic field inside the monster? If you could somehow slice a magnetar in half and look at its internal structure, you'd see something both familiar and utterly alien. A structure that resembles a planet in some ways, but operates according to physics that has no equivalent anywhere on Earth. At the surface, there's an atmosphere of sorts, though calling it that might be generous. It's a thin layer, perhaps a few millimeters thick, of hydrogen, helium, and carbon, heated to temperatures around 2 million degrees Celsius. This atmosphere glows brilliantly in X-rays, thousands of times hotter than the surface of the sun. Yet, it's the coolest part of the magnetar. Just beneath the atmosphere lies the outer crust, a solid shell perhaps a few tens of meters thick. But this isn't crust in the sense of Earth's rocky outer layer. This is a crystalline structure of atomic nuclei, arranged in a lattice and immersed in a sea of highly compressed, degenerate electrons. The nuclei themselves are exotic. neutron-rich isotopes that don't exist on Earth because they're unstable under normal conditions. But under the crushing pressure of a magnetar, they're the most energetically favorable arrangement. As you go deeper, the pressure increases, and the atomic nuclei get progressively stranger. They pack closer and closer together, and eventually you reach a critical point called the neutron drip density. Here, the nuclei are so packed with neutrons that they can't hold them all anymore. Neutrons start to leak out, dripping from the nuclei like water from an overfull sponge. These free neutrons form a fluid that flows between the crystalline lattice of nuclei. Descending further, you reach the inner crust, and here things get truly bizarre. The nuclei, now pressed incredibly close together, start to deform. Instead of neat spheres, they get squeezed into shapes that physicists, with an endearing lack of pretension, have named after pasta. There are gnocchi, sphere-shaped nuclei packed tightly together. Squeeze them more and they merge into spaghetti, long rod-shaped structures. Compress further and you get lasagna, flat sheets of nuclear matter separated by layers of neutron fluid. This nuclear pasta, subject to pressures that would make diamond look like tissue paper, forms the transition zone between the crust and the core. And finally, at about half a kilometer depth, you reach the outer core. Here, the distinction between individual nuclei has completely broken down. What you have is a uniform fluid of neutrons, with a small fraction of protons and electrons mixed in. The density is now about twice that of an atomic nucleus, meaning that the matter is packed even more tightly than in the center of an ordinary atom. This neutron matter is a superfluid, a quantum fluid with zero viscosity. If you could somehow stir it, it would continue swirling forever, never slowing down due to friction, because there is no friction. The superfluid can flow through the incredibly narrow gaps between neutrons without any resistance, passing through barriers that would be impenetrable to ordinary matter. The protons in the core are also in an exotic state. They form a superconductor, a state where electric current can flow without resistance. In a superconductor, electrons pair up in a quantum state that allows them to move in perfect coordination, never scattering off impurities or vibrations in the material. But in a magnetar's core, it's not electrons doing this, it's protons, bound together in pairs by the same quantum effects. And what lies at the very center? We don't know for certain. At densities several times that of atomic nuclei, matter enters regimes where our understanding of physics becomes uncertain. Some models suggest the core might contain hyperons, exotic particles that include strange quarks in addition to the up and down quarks found in ordinary protons and neutrons. Others propose that matter might break down entirely into a soup of free quarks and gluons, no longer bound into individual particles. Still others suggest kaon condensates or other, even more exotic states of matter. What we do know is that this entire structure, from the surface to the core, is threaded through with an unimaginably powerful magnetic field. The field lines pierce through the crust, loop through the atmosphere, and extend into space for thousands of miles around the star. And crucially, the field is not static. It's constantly evolving, constantly changing, driven by currents flowing in the superconducting core and by the gradual rearrangement of the crust. This evolution is the key to understanding why magnetars occasionally explode with such violence. When the crust breaks, the crust of a magnetar, for all its incredible strength, has a fundamental problem. It's trying to contain something that doesn't want to be contained. Remember that the magnetic field in a magnetar is constantly evolving. In the superconducting core, electric currents flow without resistance, creating magnetic fields that twist and writhe. These fields exert tremendous forces on each other, like invisible rubber bands stretched to their breaking point. The magnetic pressure in the core can exceed the mechanical strength of the overlying crust. Think of it this way. Imagine a balloon being inflated from the inside. As more air pumps in, the rubber stretches, becoming thinner and more stressed. Eventually, if you keep inflating it, the balloon will pop. A Magnetar's crust is in a similar situation, except instead of air pressure, it's being stressed by magnetic pressure, and instead of rubber, the crust is made of the strongest solid material in the universe, a crystalline lattice of atomic nuclei, bound together by the electromagnetic force and crushed by gravity into densities where there's essentially no empty space left. For a while, the crust can accommodate the stress. Crystal structures can actually support quite a lot of distortion before they fail. The nuclei in the crust can shift slightly, adjusting their positions to balance the magnetic forces. The crust can bend and warp, creating subtle changes in the Magnetar's shape, making it slightly oblate, slightly lumpy. But there's a limit. Eventually, somewhere in the crust, the stress becomes too much. A crystalline plane fails. A crack forms. And when a Magnetar's crust cracks, it doesn't do so quietly. The crack propagates at speeds approaching the speed of sound in the material, which in something this dense is a significant fraction of the speed of light. In a fraction of a second, the crack can split the crust across distances of several kilometers. The surface of the Magnetar suddenly rearranges itself, dropping or rising by perhaps a centimeter or two, adjusting to a new equilibrium. On a human scale, a centimeter seems trivial. But when that centimeter of movement happens across the surface of an object, with the mass of 1.5 suns, compressed into a sphere 12 miles across, the energy released is staggering. On Earth's seismometers, if we somehow could measure it, this event would register as an earthquake with a magnitude of about 23. The Chilean earthquake of 1960, the most powerful earthquake in recorded history, measured magnitude 9.5. Each whole number increase in magnitude represents about 30 times more energy. A magnitude 23 event releases incomprehensibly more energy than any earthquake in Earth's history. But the true power of a Magnetar starquake isn't in the crustal movement itself. It's in what that movement does to the magnetic field. When the crust cracks and rearranges itself, the magnetic field lines anchored in that crust are suddenly yanked out of position. The field, previously in a somewhat stable configuration, gets violently twisted. This is similar to what happens when you twist a rubber band. Energy gets stored in the twisted configuration, and if you let go, the rubber band will snap back, releasing that stored energy. In a Magnetar, the twisted magnetic field doesn't just snap back. The energy release accelerates charged particles to nearly the speed of light. These particles spiral along the magnetic field lines, emitting synchrotron radiation. The magnetic field is so strong that this radiation comes out at incredibly high energies in the X-ray and gamma-ray parts of the spectrum. More dramatically, the rearrangement of the field can create bubbles or clouds of hot plasma that erupt from the Magnetar's surface. These plasma clouds, trapped by the magnetic field, expand and cool, creating the prolonged tails of emission that can last for minutes after the initial burst. The December 2004 event from SGR 1806, 2O, the one that disturbed Earth's atmosphere, probably resulted from one of these giant starquakes. The initial spike, the 0.2 of a second flash that released 250,000 years worth of solar energy, marked the moment when the crust cracked and the magnetic field violently reorganized. The following minutes of emission came from hot plasma ejected during that reorganization, slowly cooling and radiating away its energy. But starquakes aren't the only way magnetars announce their presence. In recent years, astronomers have discovered that magnetars are responsible for one of the most mysterious phenomena in astronomy: fast radio bursts. The mystery of fast radio bursts. In 2007, an astronomer named Duncan Lorimer was sifting through archival data from the Parkes Radio Telescope in Australia when he noticed something strange. Buried in observations from 2001 was a brief, incredibly bright pulse of radio emission, lasting just a few milliseconds. The pulse was so bright, it stood out clearly even in data that had been sitting unanalyzed for years. What made this pulse particularly interesting was its dispersion measure, a property that tells you how much the signal has been scattered by interacting with free electrons during its journey. The dispersion measure of this pulse indicated it had traveled through an enormous amount of material, far more than exists between us and the edge of our galaxy. This signal, it seemed, had come from somewhere in the intergalactic depths, possibly billions of light years away. If the pulse really was extragalactic, then the amount of energy it carried was staggering. In just a few milliseconds, the source had released as much energy as the sun puts out in an entire day. What could possibly create such a burst? Over the following years, more of these bursts were discovered. Astronomers called them fast radio bursts, or FRBs. Most seemed to be one-off events, single bursts that never repeated. But a few sources intriguingly did repeat, firing off multiple bursts over weeks or months. The bursts showed patterns in their timing, in their brightness, in their polarization, all of which provided clues to their origin. The problem was that nobody could figure out what was creating them. Proposed explanations ranged from neutron-star collisions to evaporating black holes to, in a few speculative papers that most scientists didn't take seriously, alien civilizations. The bursts were so short and so energetic that they seemed to require something incredibly compact and incredibly powerful. The breakthrough came on April 28, 2020. Astronomers using a telescope array called CHIME, the Canadian Hydrogen Intensity Mapping Experiment, detected a radio burst from a source within our own galaxy. The burst came from the direction of a known Magnetar, SGR 1935 plus 2154, located about 30,000 light-years away in the constellation Vulpecula. By cosmic standards, 30,000 light-years is practically next door. It's close enough that astronomers could study the burst in detail, comparing it to the much more distant FRBs. The burst from SGR 1935 plus 2154 showed all the hallmarks of the extragalactic FRBs: the short duration, the bright pulse, the characteristic sweep of frequencies. It was thousands of times weaker than the typical extragalactic FRB, but that made sense given how much closer it was. If you placed this burst at the distance of a typical FRB, billions of light-years away, it would look exactly like the mysterious signals that had been puzzling astronomers for years. For the first time, astronomers had direct evidence that at least some FRBs come from magnetars. The question was, how? The answer appears to involve the same magnetic field that creates the giant flares, but operating in a slightly different way. Instead of a full crustal crack, smaller disturbances in the crust or in the magnetosphere above the magnetar's surface can create intense, localized regions where charged particles are accelerated to nearly the speed of light. These particles, spiraling in the intense magnetic field, can emit coherent radio emission, with all the waves oscillating in phase like the light from a laser. This coherent emission can be extraordinarily bright because instead of individual particles radiating independently, they're all radiating together, creating a signal that's much stronger than you'd get from random, incoherent emission. The process is similar to what happens in a maser, the microwave equivalent of a laser, except here it's happening in conditions more extreme than anything we can create in a laboratory. Recent observations have added fascinating details to this picture. In 2024, astronomers studying FRB 20201, one of the most active repeating FRBs, found evidence that this burst might be coming from a magnetar in a binary system, orbiting around a companion star. As the magnetar moves in its orbit, it passes through different regions of the stellar wind from its companion. This changing environment affects how the radio bursts propagate, creating variations in their polarization and other properties. The idea of binary magnetars opens up new possibilities. If a magnetar is accreting material from a companion star, that material carries angular momentum that can spin up the magnetar, keeping it rotating rapidly. It can also feed the magnetic field, potentially maintaining the field strength longer than would be possible for an isolated magnetar. And the interaction between the magnetar and its companion stellar wind creates a complex dynamic environment that might be particularly conducive to producing fast radio bursts. Studies of where FRBs occur in the universe have provided additional insights into magnetar formation. In 2024, a team using the Deep Synoptic Array, a collection of radio dishes in California, mapped the locations of 70 FRBs within their host galaxies. They found that FRBs tend to occur in spiral galaxies, in regions where stars are actively forming. This makes sense if FRBs come from magnetars, because magnetars are young neutron stars, and they should be found in the same regions where massive stars are still being born. But the distribution isn't uniform. Some FRBs come from the outskirts of galaxies, far from the main regions of star formation. This might mean that some magnetars receive kicks when they're born, high-speed impulses from asymmetries in the supernova explosion that send them flying through space at hundreds of kilometers per second. Over millions of years, a kicked magnetar could travel far from its birthplace, ending up in the quiet suburbs of its galaxy, or even in intergalactic space. The connection between magnetars and FRBs has fundamentally changed how astronomers think about both phenomena. Before 2020, FRBs were a complete mystery. Now they're recognized as a powerful diagnostic tool for studying magnetars and the extreme physics that governs them. By studying the properties of FRBs, the timing between bursts, the polarization of the radio waves, the dispersion measures, astronomers can probe the magnetic field structure around magnetars, the density of material in their environments, and the mechanisms that power these extraordinary outbursts. What would happen if you approached one? Let's engage in a thought experiment. Suppose you had a spacecraft that was somehow impervious to radiation and equipped with engines powerful enough to counteract the gravity of a neutron star. You decide to approach a magnetar, getting closer and closer to observe this cosmic monster firsthand. What would happen? At a distance of about 1,000 kilometers, roughly 600 miles, you're still far enough that your spacecraft's instruments are working normally. You can look out the window, if there is one, and see the magnetar as a small, intensely bright point of light, glowing white-hot in X-rays. Your ship's sensors detect powerful radio emissions, the signature of charged particles spiraling along magnetic field lines high above the magnetar's surface. The magnetic field at this distance is already stronger than anything on Earth, measuring perhaps 100,000 Gauss. If you had a compass, it would spin wildly, trying to align itself with field lines that are twisting and shifting. Any loose, metallic objects would be pulled toward the magnetar, not by gravity alone, but by magnetic forces acting on the atoms within the metal. As you move closer, Passing 500 kilometers, the field strength climbs into the millions of Gauss. Now something strange begins to happen. The atoms in your spacecraft's hull start to feel the influence of the field. Normally, atoms are roughly spherical or at least symmetrical, but the field is beginning to distort their electron clouds, squeezing them in one direction while allowing them to expand in others. At 300 kilometers, the field reaches tens of millions of Gauss. Your instruments are starting to malfunction. Electronic circuits, which depend on the precise behavior of electrons moving through semiconductor materials, no longer work correctly because those electrons are being forced into new configurations by the magnetic field. The chemistry of your body's cells, if you weren't protected by some kind of shielding, would start to go wrong. Enzymes that normally facilitate biochemical reactions would lose their shape, their active sites distorted beyond recognition. You descend to 100 kilometers, and the field is now approaching 1 billion Gauss. At this distance, something truly remarkable happens. Light itself begins to behave strangely. Photons coming from the Magnetar split into two separate photons with different energies and different polarizations, or they merge. Two photons becoming one. The vacuum of space around you has become birefringent, acting like a crystal that bends and separates light into different components. If you were somehow able to shine a flashlight at the Magnetar from this distance, the beam wouldn't travel in a straight line. It would curve, bent by the magnetic field's influence on the electromagnetic waves that make up the light. The straight line path that light normally follows through empty space no longer applies. Space itself has different properties in different directions, no longer homogeneous and isotropic, but structured and oriented by the magnetic field. At 10 kilometers from the surface, the field exceeds 10 billion Gauss. Every atom in your vicinity, from the hydrogen in any water tanks to the iron and structural components, has been deformed into a long, thin cylinder. The electron orbits that normally exist in neat, quantum mechanically determined shapes have been crushed and stretched along the magnetic field lines. If you had a periodic table with you, you could throw it away. The elements no longer behave according to their familiar chemical properties, because those properties depend on electron orbital shapes that simply don't exist in these conditions. And at this point, you'd notice something else: gravity. At 10 kilometers from a Magnetar center, the gravitational acceleration is about 100 billion times stronger than at Earth's surface. If you weren't in a spacecraft actively using engines to counteract this pull, you'd be accelerating toward the Magnetar at 1,000 billion meters per second. The tidal forces, the difference in gravity between your head and your feet, would exceed anything survivable. You'd be stretched and compressed, spaghettified in the same way that objects falling into black holes are torn apart by tidal stress. But let's say your theoretical spacecraft can somehow handle even these forces. You descend the final few kilometers to the surface. The magnetic field strength peaks at 100 billion Gauss, or perhaps even 1 trillion Gauss. At these intensities, the fundamental forces that govern matter begin to compete with each other in new ways. The electromagnetic force, amplified by the field, becomes comparable in strength to the nuclear forces binding protons and neutrons together. If you could touch the surface, which is glowing at millions of degrees and harder than any material in the universe, you'd find it's vibrating slightly, humming with starquakes that propagate through the crust like waves on a bell. Every few years, a major quake might split the surface, releasing energy that would vaporize anything nearby in a flash of gamma rays. But here's a curious fact that often gets mentioned about magnetars. There's a popular claim that a magnetar's magnetic field could strip the iron from your blood from half the distance to the moon. Is this true? The answer is no, and it's actually a useful illustration of how we can check scientific claims rather than accepting them at face value. The magnetic field from a magnetar does drop off with distance, following what's called a dipole field pattern. The field strength decreases proportional to the cube of the distance. By the time you're 1,000 kilometers away, it's dropped to about 100,000 Gauss. At 10,000 kilometers, it's down to 100 Gauss. At the Earth-Moon distance of 380,000 kilometers, the field would be nearly negligible, less than the field from a refrigerator magnet. Your blood wouldn't be affected at all. You wouldn't even notice the magnetic field at that distance. The credit card myth, the idea that a magnetar could erase your credit card from lunar distance, is a fun story, but not physically accurate. You'd need to be within a few hundred kilometers before magnetic effects became significant. The strange physics of magnetar matter. The conditions inside and around a magnetar push physics into regimes we can barely study in laboratories on Earth. Let's explore some of the truly bizarre effects that emerge when matter encounters magnetic fields measured in the trillions of Gauss. First, consider what happens to atoms. In a normal environment, an atom's energy levels are determined by quantum mechanics. Electrons can only occupy certain discrete energy states, and the gaps between those states determine which wavelengths of light the atom can absorb or emit. This is why each element has a characteristic spectrum, a unique fingerprint of bright and dark lines that astronomers use to identify elements in distant stars. In a powerful magnetic field, those energy levels shift. The effect is called Zeeman splitting, and it's actually observable in the relatively weak magnetic fields of sunspots, which measure a few thousand Gauss. In those conditions, spectral lines split into 2 or 3 components, slightly separated in wavelength. But in a magnetar's trillion Gauss field, Zeeman splitting becomes extreme. Energy levels that were separated by small amounts in zero field might now be split by factors of hundreds or thousands. New energy levels appear that don't exist at all in the absence of the field. The entire quantum structure of the atom is rearranged. For hydrogen, the simplest atom, this means that the familiar energy levels corresponding to different electron orbits get compressed and shifted. States that normally have spherical symmetry become cylindrical. The atom, which would normally be about 1/10 billionth of a meter in radius, becomes stretched to perhaps 200 times that length in the direction along the magnetic field, while shrinking to a tiny fraction of its normal size perpendicular to the field. Heavier atoms with more electrons experience even more complex rearrangements. Each electron feels the magnetic field's influence, and the interactions between electrons, which normally dominate atomic structure, have to compete with the magnetic field's organizing influence. Computer simulations of atoms in magnetar strength fields show structures that look nothing like the neat orbital shells shown in chemistry textbooks. This has profound implications for the magnetar surface. The atmosphere, that thin layer of hot gas sitting above the solid crust, consists of atoms in these extremely distorted states. When these atoms emit light, they produce spectra that are completely unlike anything we see from normal stars. Absorption lines appear at unexpected wavelengths. The polarization of the light, the direction in which the electromagnetic waves oscillate, is strongly affected by the magnetic field. By carefully studying the X-ray spectra from magnetars, astronomers can actually map the magnetic field structure. Features in the spectrum correspond to specific field strengths, allowing researchers to determine not just the overall field strength, but how the field varies across the star's surface and how it changes with altitude above the surface. Some magnetars show evidence of tangled, complex magnetic fields with regions of different strengths. Others appear to have more organized dipole fields, with field lines emerging from one magnetic pole and curving around to enter at the other pole, similar to Earth's magnetic field but billions of times stronger. Now let's consider the effects on the vacuum itself. In quantum field theory, what we call empty space isn't truly empty. It's filled with a seething background of virtual particles, electron-positron pairs that briefly pop into existence, exist for a tiny fraction of a second, and then annihilate back into the vacuum. These quantum fluctuations are a fundamental prediction of quantum mechanics combined with special relativity, and they've been confirmed by countless experiments. In a weak magnetic field, these virtual particles don't have much effect. They appear and disappear too quickly to influence anything. But in a Magnetar's field, something remarkable happens. The virtual electron-positron pairs, which carry electric charge, feel the magnetic field's influence. They become polarized, aligning themselves with the field during their brief existence. This polarization of the vacuum changes how light propagates through it. Photons traveling through this magnetized vacuum split into two modes called the ordinary and extraordinary modes, which propagate at slightly different speeds and with different polarizations. It's as if empty space has become birefringent, like a calcite crystal that splits light beams into two separate paths. Astronomers hunting for this effect, called vacuum birefringence, analyzed X-ray observations from a magnetar called RX Joan 8565 3754. In the data, they found evidence of polarized light that had clearly passed through a region where vacuum birefringence was operating. This was a major discovery because it represented the first clear observational confirmation of a quantum electrodynamics effect that had been predicted theoretically for decades but had never been seen in nature. But the strangeness doesn't stop there. In ultra-strong magnetic fields, photons can split in a different way. A single high-energy photon entering a strong magnetic field can spontaneously split into two lower-energy photons. Or the reverse can happen. Two photons can merge into one higher-energy photon. These processes, called photon splitting and photon merging, are forbidden in the vacuum we experience on Earth, but become possible in magnetar fields. The result is that the radiation environment around a magnetar is incredibly complex. Photons are constantly being created, destroyed, split, and merged as they try to escape from near the surface. The spectrum we observe, the distribution of photons at different energies, reflects all of these processes acting together. Untangling what's happening requires sophisticated models that account for both the quantum behavior of photons and the influence of the curved spacetime around the neutron star. Even more exotic effects become possible as you consider higher and higher field strengths. Some theoretical work suggests that at field strengths just beyond what current magnetars produce, perhaps around 1,000 trillion Gauss, the vacuum might undergo a phase transition, similar to how water freezes into ice. This is speculative, well beyond what we can currently test, but it represents the kind of frontier physics that magnetars allow us to explore. The interior of the magnetar provides its own set of bizarre conditions. The neutron superfluid in the outer core, flowing without viscosity, can support quantum vortices, tiny whirlpools in the fluid that carry quantized amounts of angular momentum. As the magnetar spins, these vortices arrange themselves in a regular array, all pointing along the rotation axis, creating a sort of quantum lattice, rotating with the star. But the magnetar is gradually slowing down, losing rotational energy to the magnetic field and to the emission of electromagnetic radiation and particle winds. As it spins down, the superfluid interior, which has less friction than the crust, tends to keep spinning at its original rate. This creates a differential rotation between the superfluid core and the solid crust. Eventually, the lag becomes large enough that quantum vortices in the superfluid suddenly move outward, transferring angular momentum to the crust in an event called a glitch. Glitches are observed in many neutron stars, including Magnetars. The star's rotation suddenly speeds up slightly, as if someone had given it a push. Then, it gradually settles back down as the interior and exterior come back into equilibrium. Some Magnetars show anti-glitches, where the rotation suddenly slows instead of speeding up. These are harder to explain and might be related to crustal cracking or magnetic field reorganization. The magnetic field itself isn't static on longer timescales. Over thousands to millions of years, the field gradually decays. Currents in the superconducting core that maintain the field slowly dissipate as the core cools. The field strength drops, and eventually the magnetar transitions into a more ordinary neutron star, or possibly into a pulsar, a rapidly rotating neutron star that emits regular pulses of radio emission as it spins. This evolutionary track helps explain why magnetars are relatively rare. Despite the Milky Way containing an estimated 1 billion neutron stars accumulated over the galaxy's 10 billion year history, we've only identified about 30 confirmed magnetars. They represent a brief phase in a neutron star's life, the first tens of thousands to perhaps 100,000 years after formation, when the magnetic field is at its peak. After that, they fade into the population of ordinary neutron stars, their brief time as cosmic monsters at an end. The heat from within. One of the puzzling features of magnetars, something that initially helped identify them as unusual objects, is their temperature. They're hot, far hotter than they should be. An ordinary neutron star, freshly born in a supernova, starts out incredibly hot, with interior temperatures exceeding 100 billion degrees. But it cools rapidly. With no nuclear fusion to generate heat and an enormous surface area relative to its volume, a neutron star radiates away its thermal energy quickly. Within 1,000 years, its surface temperature drops from hundreds of millions of degrees to about 1 million degrees. After 1 million years, it's cooled to a few 100,000 degrees and becoming difficult to detect in X-rays. Magnetars don't follow this cooling curve. Their surface temperatures, measured from their X-ray emission, range from about 2 million to 10 million degrees, much hotter than expected for neutron stars of their estimated ages. Some magnetars appear to be thousands or even tens of thousands of years old, yet they're still blazing hot, radiating away energy at rates far exceeding what can be explained by residual heat from their formation. Where is this energy coming from? The answer lies in the magnetic field itself. A magnetar's magnetic field contains enormous energy. The energy density in a field measuring 100 billion Gauss is roughly comparable to the energy density in matter at nuclear densities. In other words, the magnetic field carries as much energy as the matter it's permeating. For the magnetic field threading through a typical magnetar, the total energy stored is about 10 to the 47th power ergs, roughly equivalent to the entire energy output of the Sun over its 10 billion year lifetime. As the magnetic field slowly decays and reorganizes, this energy gets converted into heat. Electric currents flowing in the crust and core gradually dissipate, warming the star. Magnetic field lines twist and reconnect, releasing energy in the process. The field presses outward on the crust, creating stresses that generate heat as the material deforms. Computer models of magnetar thermal evolution show that this magnetic heating can keep the star warm for tens or even hundreds of thousands of years. The rate of heating depends on how quickly the field decays and how efficiently the field energy converts into thermal energy. Different models make different assumptions about the electrical resistivity of the crust and core, about the viscosity of the fluid in the interior, about the rate of magnetic field reconnection. Observations of multiple magnetars at different ages allow astronomers to test these models. Young magnetars, just a few thousand years old, should be at their hottest, with strong magnetic fields still at their peak. Older magnetars, tens of thousands of years old, should have cooled somewhat and have weaker fields as the field energy gradually gets radiated away. One fascinating case study is the object known as Swift-Jones 8349 0846. This magnetar was discovered in 2011 when it underwent an outburst, suddenly brightening in X-rays. Observations showed it was extraordinarily hot, with a temperature around 170 million degrees Kelvin, by far the hottest magnetar ever recorded. The temperature was so high that it challenged theoretical models, requiring either an exceptionally young age or some additional heating mechanism beyond magnetic field decay. Further observations revealed that Swift-Jones 8349 0846 lies within a supernova remnant, the expanding shell of debris from the explosion that created it. By measuring the size and expansion rate of that remnant, astronomers estimated the magnetar's age at about 6,000 to 10,000 years. That's young for a neutron star, consistent with its high temperature, but it still requires very efficient conversion of magnetic energy into heat to explain the observations. The outburst behavior itself provides additional heating. When a magnetar undergoes a starquake and releases a giant flare, the energy doesn't all escape into space. Some of it gets deposited in the star's outer layers, heating them. The surface temperature can rise significantly during and after an outburst, then gradually decline over months to years as the heat radiates away. Monitoring magnetars over time has shown this pattern repeatedly. A magnetar will be relatively quiet, emitting steady X-rays at a predictable level. Then it undergoes an outburst, and its X-ray brightness increases by factors of hundreds or thousands. Over the following months, the brightness gradually fades, though often not back to the exact pre-outburst level. The star seems to settle into a new equilibrium state, slightly brighter or sometimes slightly dimmer than before. What triggers these outbursts isn't completely understood. One possibility is that they're essentially unpredictable, resulting from random stresses in the crust that accumulate until something breaks. Another possibility is that they're cyclic, related to long-term evolution of the magnetic field that creates regular stress patterns. Some magnetars do show quasi-periodic outburst behavior, with events separated by a few years, suggesting there might be some underlying regularity. The cooling process also depends on what's happening in the magnetar's interior. The dense matter at the core can undergo phase transitions as it cools. Neutrons can pair up to form a superfluid. Protons can pair up to form a superconductor. These transitions release latent heat, similar to how water releases heat when it freezes into ice, warming the star and slowing its cooling. Different theoretical models of neutron star interiors predict different transition temperatures and different amounts of latent heat. By measuring the cooling rates of multiple neutron stars and magnetars, astronomers can potentially constrain which models are correct. Learning about the exotic states of matter that exist at nuclear densities and beyond. Recent X-ray observations with instruments like NISCR, the Neutron Star Interior Composition Explorer aboard the International Space Station, have provided unprecedented precision measurements of neutron star surface temperatures and how they change over time. NISR can detect temperature variations of just a few %, allowing astronomers to track cooling in near real time and to map temperature variations across the star's surface. These observations have revealed that magnetar surfaces aren't uniformly hot. There are hotspots, regions where the magnetic field emerges from the surface and where heating is concentrated. There are cooler regions, possibly corresponding to magnetic poles, or regions where the field is primarily parallel to the surface. By watching how these hotspots move as the magnetar rotates and how they evolve as the star cools, astronomers can learn about the magnetic field's three-dimensional structure and about the processes heating the surface. How many magnetars exist? One of the fundamental questions about magnetars is simply, how common are they? In our own Milky Way galaxy, we've positively identified about 30 objects as magnetars based on their X-ray emission, their bursting behavior, or their association with supernova remnants. But that number is almost certainly a significant undercount. Many magnetars are likely too faint for us to detect, especially if they're old and their magnetic fields have decayed substantially. Others might be hidden behind dense clouds of gas and dust that absorb their X-ray emission before it can reach us. Still others might be on the far side of the galaxy, too distant for current telescopes to pick up their signals. Estimating the true population requires some detective work. Astronomers start with what they can observe directly, the rate at which magnetars undergo detectable outbursts. Over the past few decades of systematic monitoring, we've seen roughly one magnetar outburst every year, or two, in our galaxy. But not all magnetars burst frequently. Some seem to go decades between major outbursts. Others might be in quiescent states, no longer producing detectable bursts at all. By combining the observed outburst rate with theoretical models of how often magnetars should burst and how long they remain active, astronomers can estimate the total population. The calculation suggests there might be several hundred to perhaps 1,000 active magnetars in the Milky Way at any given time, with active meaning they still have strong enough magnetic fields and enough stored energy to occasionally produce outbursts. But the total number of magnetars that have ever existed in the galaxy is much larger. Remember that the magnetar phase is temporary. After somewhere between 10,000 and 100,000 years, the magnetic field decays enough that the star transitions into a more ordinary neutron star, or pulsar. Given that the Milky Way has been forming stars for about 10 billion years, and that massive stars which can become magnetars are born at a rate of perhaps one every 50 to 100 years, the total number of objects that have passed through a magnetar phase might be in the millions. Where are all these former magnetars? They're still out there, just no longer recognizable as magnetars. They've joined the vast population of ordinary neutron stars, invisible unless they happen to be rotating and beaming radio waves in our direction as pulsars. Some might have accreted enough material to spin up into millisecond pulsars, objects rotating hundreds of times per second. Others might be slowly drifting through the galaxy in isolation, too cool and dim to detect. Understanding the magnetar population is complicated by the fact that we don't fully understand what fraction of neutron stars become magnetars in the first place. Is every neutron star born with an ultra-strong magnetic field that decays over time? Or do only certain neutron stars, formed under specific conditions, ever become magnetars? The evidence suggests the latter. The distribution of neutron star magnetic field strengths shows a clear separation between magnetars, with fields from 10 to the 14th to 10 to the 15th Gauss, and ordinary pulsars, which typically have fields around 10 to the 12th Gauss. This hundredfold gap suggests there are two distinct populations rather than a continuous distribution. This points toward a formation mechanism that either works very efficiently, creating magnetars with ultra-strong fields, or doesn't work at all, producing ordinary neutron stars with more modest fields. The binary formation scenario, where mass transfer from a companion star spins up the progenitor before collapse, might explain this dichotomy. Stars in binary systems might become magnetars, while isolated massive stars become ordinary neutron stars. The discovery of HD 45166, the massive magnetic star that appears destined to form a magnetar in the future, provides a critical piece of evidence. HD 45166 is in a binary system, consistent with the idea that binary evolution plays a role. As more pre-magnetar candidates are identified and studied, we should be able to test this hypothesis more rigorously. Another approach to estimating the magnetar population is through fast radio bursts. If FRBs do come primarily from magnetars, then the rate at which we detect FRBs can tell us something about how many magnetars exist, not just in our galaxy, but throughout the universe. Current estimates suggest we should be detecting roughly 1,000 FRBs per day across the entire sky, though most go undetected because telescopes aren't looking in the right direction at the right time. If each FRB producing magnetar fires off bursts at a certain average rate, we can work backwards to estimate how many such objects must exist. The calculations are tricky because they depend on assumptions about burst rates, about how long magnetars remain capable of producing FRBs, and about how the FRB producing magnetar population has evolved over cosmic time. Different assumptions lead to population estimates ranging from millions to billions of FRBs producing magnetars across the observable universe. One intriguing possibility is that virtually all active magnetars produce FRBs, just at different rates. The magnetars in our galaxy that we've studied in detail, like SGR 1935 plus 2154, produce radio bursts relatively rarely. But perhaps there are magnetars in other galaxies that burst much more frequently, accounting for the thousands of FRBs we detect. Alternatively, maybe FRB production is a brief phase that magnetars pass through at a specific time in their evolution. Perhaps young magnetars in their first few thousand years produce frequent FRBs, while older magnetars produce them rarely or not at all. This would affect the population estimates significantly because it would mean the FRB producing population is much smaller than the total magnetar population. As surveys like KIME continue to detect and localize FRBs, we're building up a statistical sample that will eventually constrain these questions. By mapping where FRBs occur in their host galaxies, what types of galaxies produce the most FRBs, and how the FRB rate changes with cosmic time, we'll learn not just about fast radio bursts, but about the magnetars that produce them, unanswered questions, and future discoveries. Despite the tremendous progress in understanding magnetars over the past few decades, fundamental questions remain. These objects continue to challenge our understanding of physics in extreme environments, and each new observation seems to raise as many questions as it answers. One of the biggest unknowns is the upper limit on magnetic field strength. We've observed magnetars with fields approaching 10 to the 15th Gauss, but theoretical models suggest that even stronger fields might be possible. Could there be supermagnetars with fields exceeding 1,000 trillion Gauss? At those intensities, the magnetic pressure would exceed the pressure from the star's own gravity, potentially leading to completely new behaviors. Some theoretical work suggests that the crust of a neutron star simply cannot support magnetic fields beyond a certain limit, somewhere around 10 to the 16th Gauss. Above that threshold, the magnetic stress would exceed the mechanical strength of even the ultra-dense crustal material, causing continuous cracking and preventing the field from ever reaching higher values. But we don't know for sure because we've never observed such an object. Another mystery involves the geometry and evolution of the magnetic field itself. Early models assumed magnetars had simple dipole fields with two magnetic poles like Earth's field, but billions of times stronger. More recent observations and simulations suggest the reality is far more complex. Magnetars might have twisted toroidal fields, rings of magnetic fields wrapped around the star's equator beneath the crust. They might have higher-order multiple components, regions where the field reverses direction multiple times across the surface. Understanding the field geometry is crucial because it affects everything else about the magnetar. How quickly the field decays, how the star spins down, where and when starquakes occur, and how efficiently the magnetar can produce FRBs, or giant flares. Current X-ray observations provide some constraints on surface field structure, but they can't directly probe the interior field configuration. That requires indirect methods, comparing observations to detailed models and seeing which field geometries best explain what we see. The mystery of anti-glitches remains unsolved. Most neutron stars show glitches, sudden spin-ups caused by the superfluid interior transferring angular momentum to the crust. But some magnetars show the opposite behavior, suddenly spinning down instead of up. The standard explanation for glitches doesn't work for anti-glitches. Perhaps they're caused by crustal cracking that releases angular momentum instead of adding it. Or perhaps they involve changes in the magnetic field structure that couple to the star's rotation in unexpected ways. We need more observations and more sophisticated models to understand what's happening. The connection between magnetars and other exotic neutron star phenomena is another rich area for investigation. Some neutron stars emit low-frequency radio pulses like ordinary pulsars, but with erratic timing and occasional giant pulses thousands of times brighter than average. These rotating radio transients might be magnetars viewed from certain angles, or they might represent a separate class of objects. Figuring out the relationship will help complete the picture of neutron star diversity. There's also the question of magnetar lifetimes. We think magnetars gradually fade into ordinary neutron stars as their fields decay. But we've never observed this transition happening. How long does it take? Does the transition happen gradually over tens of thousands of years, or relatively quickly once the field drops below some critical threshold? Do former magnetars retain any distinctive features that might let us identify them in the existing neutron star population? Future observatories will help answer these questions. The Einstein probe, a Chinese-European mission that launched in early 2024, is designed to scan the X-ray sky continuously, looking for transient events like magnetar outbursts. With its wide field of view and rapid response capability, it should catch many more outbursts than previous missions, allowing us to study the full range of magnetar behavior. The Square Kilometre Array, a next-generation radio telescope currently under construction in Australia and South Africa, will be far more sensitive than existing instruments to fast radio bursts. It should be able to detect FRBs from magnetars in our own galaxy, even during quiet periods, not just during the most powerful bursts. This will help establish definitively how many magnetars produce FRBs and how often. And missions like NICER continue to provide exquisitely precise measurements of neutron star properties. By mapping surface temperature variations, measuring spin rates to high precision, and detecting subtle changes over time, these observations constrain theoretical models and reveal new aspects of magnetar behavior. Perhaps the most exciting possibility is that we might observe the birth of a new magnetar. If astronomers can identify more systems like HD 45166 magnetar progenitors that will explode in the relatively near future by astronomical standards, we could potentially catch the formation event. Watching a magnetar form and evolve through its first years would provide invaluable data about the dynamo mechanism, the field's initial configuration, and how quickly the star settles into a stable state. And there's always the possibility of truly unexpected discoveries. Before 2004, nobody anticipated that magnetar flares could be so powerful they'd affect Earth's atmosphere from 50,000 light-years away. Before 2020, the connection between magnetars and FRBs was speculative at best. What other surprises might magnetars have in store? Perhaps we'll find evidence that magnetars can somehow maintain their ultra-strong fields for much longer than current models predict. Perhaps we'll discover that some black holes form directly from magnetars when they accrete enough material to exceed the neutron star mass limit. Perhaps we'll find magnetars with even more extreme properties, objects that challenge theoretical models in new ways. Magnetars in the cosmic context. Let's zoom out and consider where magnetars fit in the larger context of cosmic evolution and the extreme objects that populate our universe. Magnetars represent, in some sense, the endpoint of stellar evolution for a specific range of massive stars. Stars are born from clouds of gas and dust that collapse under their own gravity. They spend most of their lives fusing hydrogen into helium, generating energy that pushes outward against gravity's inward pull. Eventually, they exhaust their fuel, and what happens next depends on their mass. Small stars, like our Sun, will gently shed their outer layers and fade into white dwarfs, dense Earth-sized embers supported by electron degeneracy pressure. More massive stars undergo more violent ends, exploding as supernova and leaving behind neutron stars or black holes. The most massive stars might collapse directly into black holes without exploding at all. Magnetars occupy a narrow slice of this parameter space. They come from stars massive enough to explode as core collapse supernovae, but not so massive that they form black holes directly. The progenitor star needs to have specific properties, rapid rotation, or a binary companion to spin it up, perhaps unusual chemical composition or internal mixing that affects the collapse dynamics. Only a fraction of the neutron stars born each year become magnetars. But during their active phase, magnetars are among the most energetic objects in the universe. A single giant flare from a magnetar releases more energy in a fraction of a second than the Sun will produce in hundreds of thousands of years. Over its lifetime, a magnetar might pour out energy equivalent to a substantial fraction of the rest mass energy of the Sun, all powered by the gradual decay of its magnetic field. This energy doesn't just disappear. It goes into heating the magnetar itself, into accelerating particles to relativistic speeds, into generating electromagnetic radiation across the spectrum from radio waves to gamma rays. Some of that radiation escapes into space, eventually being absorbed by interstellar gas and dust. Some of it might heat nearby gas clouds, possibly triggering or suppressing star formation in the magnetar's neighborhood. The particle winds and radiation from magnetars, while not as powerful as the jets from active galactic nuclei or the winds from massive stars, still contribute to the energy budget of the interstellar medium. In regions of active star formation, where multiple massive stars are being born and dying in relatively rapid succession, magnetars might play a role in regulating the pace at which new stars form. There's also the question of magnetars' role in the chemical enrichment of the cosmos. While supernovae are the primary factories for heavy elements, the extreme environment surrounding a magnetar, with its relentless flux of neutrinos and high-energy particles, might facilitate unique nucleosynthesis pathways. In the moments following a magnetar's birth, the intense magnetic field can influence the expansion of the supernova shock wave, potentially creating pockets of space enriched with rare isotopes that would not form under ordinary conditions. These elements eventually find their way into the next generation of stars and planets, meaning that the atoms in your very own body might carry the faint ancient signature of a magnetic monster that roared billions of years ago. As we look toward the future of our galaxy, we must realize that Magnetars are a fleeting brilliance. Within 100,000 years, a mere heartbeat in cosmic time, the magnetic dynamo that powers these beasts begins to falter. The currents in the superconducting core encounter resistance. The twisted field lines eventually untangle, releasing their final bursts of heat into the cold vacuum. What remains is a retired magnetar, a cold, dark sphere of neutron matter drifting through the interstellar graveyard. These silent husks likely outnumber active magnetars by a factor of 10,000 to 1. Our galaxy is littered with these invisible ghosts, objects that once warped the fabric of reality, but are now so quiet they defy detection. They are a sobering reminder that even the most terrifying power in the universe eventually yields to the steady march of entropy. Standing on the surface of our stable, gentle Earth, it is easy to feel that the laws of physics are fixed and predictable. We rely on the fact that atoms stay spherical, that light travels in straight lines, and that magnets are merely tools for holding notes on a fridge. But Magnetars teach us that our experience is a sheltered one. We live in a low-energy suburb of the universe, far from the cosmic monsters that rewrite the rulebook of reality. By studying these objects, we aren't just cataloging oddities in the sky. We are testing the very limits of what nature allows. We are peering into a laboratory where the vacuum acts like a crystal, where matter turns into pasta, and where a single starquake can be felt across the breadth of the Milky Way. Magnetars remind us that the universe is far stranger, far more energetic, and far more interconnected than we ever dared to imagine. Starquakes and giant flares. The universe is often perceived as a silent, cold void, a place where the laws of physics play out in a slow, predictable dance. But when we turn our gaze toward magnetars, that perception is shattered. We find ourselves facing objects that defy every earthly intuition about stability and matter. To understand the magnetar, you must first understand that it is not just a dead star. It is a living, breathing dynamo of magnetic energy. And like the Earth, it has a solid outer layer, a crust. However, the similarities end there. While Earth's crust is made of tectonic plates of rock and silicate, a magnetar's crust is a crystalline lattice of iron nuclei, compressed by gravity to densities 1 billion times that of steel. This material is so dense that a teaspoon of it would weigh billions of tons. But even this ultra-rigid structure has a breaking point. When the internal magnetic field of a magnetar becomes too twisted, wound up like a rubber band stretched beyond its physical limit, it exerts a mechanical stress on this iron crust that is trillions of times stronger than anything we can produce in a laboratory. Eventually, the crust cannot hold. It snaps. This cataclysmic rupture is what we call a starquake. A starquake is the progenitor of the most energetic events ever recorded in the cosmos outside of supernovae, giant flares. These are not merely large solar flares. They are cosmic events of such magnitude that they redefine our understanding of power. To date, humanity has been fortunate enough to witness only 3 of these truly giant flares from within our own galaxy. The first in 1979, the second in 1998, and the most terrifyingly powerful one on December 27, 2004. This 2004 event originated from SGR 186. Juicero, a magnetar located roughly 50,000 light-years away. To put that in perspective, that is on the complete opposite side of the Milky Way galaxy. Yet, despite this staggering, unimaginable distance, the flare was so powerful that it physically affected Earth's atmosphere. At 21:30 UTC, a wave of gamma radiation hit our planet. It ionized the upper layers of our ionosphere, momentarily expanding it, as if our planet had been hit by a solar storm from our own sun, which is millions of times closer. Every X-ray satellite in orbit, including those pointed away from the source, had its sensors completely saturated. It was a blinding flash in the dark of the cosmos. If this Magnetar had been located within 10 light-years of Earth, a stone's throw in galactic terms, it would have likely caused a mass extinction event. The sheer intensity of the gamma radiation would have stripped away our ozone layer instantly, leaving life on the surface vulnerable to the sun's ultraviolet radiation, and potentially causing massive nitrogen oxide formation in the atmosphere, leading to acid rain and global cooling. This realization shifted Magnetars from being mere astronomical curiosities to being recognized as potential galactic hazards. The physics behind these flares is a violent dance between magnetic reorganization and crustal cracking. As the magnetic field lines move within the star, they are frozen into the matter. Because the magnetic field is so strong, it doesn't just pass through the crust, it drags the solid crust with it. This creates immense shearing forces. Imagine trying to twist a block of solid steel with a force stronger than gravity itself. When the crust reaches its breaking point, it fractures. This fracture releases a seismic wave of energy that ripples through the star. But the real fireworks happen outside. The sudden movement of the crust triggers a massive reconfiguration of the magnetic field lines in a process called magnetic reconnection, the same process that causes solar flares on our sun, but amplified by a factor of 1 trillion. The magnetic field lines snap, break, and reconnect into a lower energy state. This snap releases a fireball of electron-positron plasma. Because the magnetic field is still present, this fireball doesn't just fly off into space. It is trapped by the magnetic field lines, creating a pulsating tail of energy. As the Magnetar rotates, this trapped fireball sweeps across the view of our telescopes like a lighthouse beam made of pure gamma radiation. This allows us to observe the effects across the entire electromagnetic spectrum, from radio waves to the most energetic gamma rays. The energy release mechanisms involved are truly mind-bending. A single giant flare from a Magnetar can release more energy in 1/10 of a second than our sun emits in 150,000 years. This isn't just a number. It's a testament to the fact that magnetic fields, when compressed to the scales found in neutron stars, become the dominant energy source in their local environment, surpassing even the nuclear fusion that powers regular stars. These events provide us with a rare, invaluable window into the internal structure of neutron stars, a place we can never visit and can barely simulate. By studying the quasi-periodic oscillations, QPOs, in the light curves of these flares, scientists can perform what is known as neutron star seismology. Just as geologists use the waves from earthquakes to map the core and mantle of the Earth, astrophysicists use the vibrations from starquakes to measure the thickness of the Magnetar's crust and the state of the superfluid matter deep within its core. We are learning that the interior of these stars may contain exotic states of matter, such as nuclear pasta, where protons and neutrons arrange themselves into sheets and strands under extreme pressure. Furthermore, the observable effects are not limited to the high-energy burst itself. These flares are often preceded or followed by a period of quiescence, where the Magnetar slowly settles back into its state, but the magnetic field remains permanently altered. This reorganization can lead to increased persistent X-ray emission or a change in the star's rotation speed. Sometimes the star suddenly speeds up, a glitch, or even more strangely, slows down, an anti-glitch. These timing anomalies are the fingerprints of the invisible magnetic hand shifting the massive weight of the star. In summary, starquakes are the ultimate expression of magnetic power. They remind us that in the universe, even the most solid surfaces are subject to the whims of invisible fields. A magnetar is a world of iron and magnetism, where the ground itself can become a weapon, and a crack in the surface can light up the entire galaxy. The sheer scale of a starquake requires us to rethink our definition of solid. On Earth, we are used to materials that have a certain elasticity or a predictable point of failure. But in the crust of a magnetar, the iron nuclei are arranged in a Coulomb lattice so tight that the shear modulus, the measure of a material's resistance to deformation, is roughly $10. Circumflex, times higher than that of the most advanced carbon fiber composites we can manufacture. When we talk about crustal cracking, we are talking about a catastrophic failure of this lattice. The magnetic field lines, which are anchored into this crust, act like invisible, incredibly stiff cables. As the magnetic field evolves, driven by the decay of the field deep within the core, it winds up. Imagine a massive, miles-thick sheet of solid diamond being twisted by a force so strong it begins to warp. For decades, the crust resists. It holds the energy back, storing it as potential elastic energy. But the magnetic field is relentless. The pressure builds at the foot points where the magnetic loops emerge from the surface. When the stress finally exceeds the breaking strength of the magnetized iron, the crust doesn't just crack. It undergoes a collective failure. This is the physics of starquakes. The displacement might only be a few millimeters or centimeters, a tiny distance for a star 20 kilometers wide. But because the density is so high, that tiny movement releases a kinetic energy equivalent to a magnitude 32 earthquake on the Richter scale. For context, the largest earthquake ever recorded on Earth was a magnitude 9.5. Because the Richter scale is logarithmic, a magnitude 32 event is not just bigger, it is trillions of times more energetic. This seismic energy is immediately converted into magnetic energy. As the crust shifts, the magnetic field lines that are frozen into it are violently jerked. This creates a massive electromagnetic pulse. This pulse propagates outward at the speed of light, but it also propagates inward, triggering further oscillations within the star's superfluid interior. This brings us to the energy release mechanisms. The primary mechanism is magnetic reconnection. When the crust snaps, the magnetic field lines are forced into configurations that are no longer stable. They short-circuit. In an instant, the energy stored in the magnetic field is converted into heat and particle acceleration. This creates a fireball of pair-produced electrons and positrons, trapped within the star's magnetosphere. This fireball is so hot, billions of degrees, that it emits primarily in the hard gamma-ray spectrum. To understand the evolution of our knowledge, we must look at the 1979 and 1998 giant flares in comparison to the 2004 event. The March 5, 1970 event was the first of its kind ever detected. It came from a source in the Large Magellanic Cloud called SGR 0526. At the time, astronomers were baffled. The burst was so intense that it was initially thought to be a nearby supernova or a new type of nuclear explosion in space. It lasted only a fraction of a second, but was followed by a series of periodic pulsations every 8 seconds, which we now know corresponds to the rotation period of the Magnetar. Then came the August 27, 1998 event from SGR 1, 99+14. This flare provided the first clear evidence that these events could physically alter the Earth's environment. It caused a measurable ionization of the Earth's nighttime ionosphere, effectively turning the night sky, in terms of radio reflectivity, into a daytime sky for a few minutes. This was a wake-up call. It proved that Magnetars, despite being thousands of light years away, were part of our local, high-energy environment. However, the December 27, 2004 event remains the gold standard for Magnetar research. The energy released in the first 0.2 seconds of this flare was more than the total energy the Sun radiates in 250,000 years. This flare didn't just affect Earth's ionosphere. It was so bright that it blinded X-ray telescopes that were not even looking in its direction. The radiation bounced off the Moon and was detected as a reflection. This allowed scientists to calculate the true peak luminosity of the event, which reached $10 circumflex 47 ergs per second. One of the most fascinating observable effects across the electromagnetic spectrum is the tail of the giant flare. After the initial spike of gamma rays, which lasts less than half a second, there is a pulsating tail that can last for several minutes. During this phase, we see the fireball cooling down. As it cools, the emission shifts from gamma rays to X-rays. Because the fireball is trapped by the magnetic field, it rotates with the star. By watching the flicker of this tail, we can see the star's rotation. But more importantly, we see harmonics, tiny, high-frequency ripples on top of the main pulse. These are the QPOs, quasi-periodic oscillations, I mentioned earlier. These ripples are the literal sound of the star ringing like a bell. By analyzing these frequencies, physicists can determine the equation of state of neutron star matter, essentially telling us how squishy or hard a neutron star is. This is information we cannot get any other way. The impact of these starquakes extends beyond just light. They are also expected to be sources of gravitational waves. While current detectors like LIGO and Virgo are primarily tuned for merging black holes, the sudden mass redistribution during a giant starquake, where trillions of tons of matter shift in a millisecond, should produce a burst of gravitational radiation. Detecting these waves would allow us to see inside the star at the moment the crust fails, providing a final confirmation of our models of crustal cracking and magnetic reorganization. In the aftermath of a giant flare, the Magnetar is not the same. The magnetic reorganization is permanent. The field has moved to a new, slightly lower energy configuration, but the process of winding up begins almost immediately again. The interior of the star is still rotating at a different speed than the crust, and the magnetic field continues to decay, putting new stresses on the iron lattice. It is a cycle of tension and release that can last for 10,000 to 100,000 years, the typical active lifetime of a magnetar before its field weakens enough that it can no longer produce these giant flares. When we observe these events, we are witnessing the most extreme seismology in the known universe. A starquake is a reminder that even the most compact, stable-looking objects in the night sky are dynamic systems governed by invisible forces. The giant flares they produce are the voices of these stars, screaming across the vacuum of space, carrying information about the very nature of matter and the limits of electromagnetism. As we look deeper into the physics of starquakes, we must address the superfluid component. Inside a magnetar, beneath the iron crust, lies a mantle of neutrons that exist in a superfluid state, meaning they flow with zero friction. However, this superfluid is quantized into millions of tiny vortices. These vortices are pinned to the crust. When a starquake occurs and the crust shifts, these vortices can suddenly unpin and move, leading to a massive transfer of angular momentum. This is the secret behind the glitches observed in the wake of flares. The interaction between the solid crust and the quantum fluid interior is one of the most complex problems in modern astrophysics, involving a mix of general relativity, quantum mechanics, and fluid dynamics. The 2004 event that affected Earth also taught us about the shielding of our planet. The fact that our ionosphere reacted so strongly to a source 50,000 light-years away suggests that a magnetar flare within our local spiral arm, say 3,000 light-years away, could be catastrophic. The gamma rays would not only ionize the air, but would break apart molecular nitrogen and oxygen, leading to the creation of nitrogen oxides. These chemicals act as catalysts that destroy ozone. A single giant flare could deplete the global ozone layer by 20% to 30% for several years. This would result in a significant increase in UV radiation reaching the ground, potentially damaging the base of the food chain, such as phytoplankton in the oceans. Furthermore, the observable effects across the electromagnetic spectrum have recently expanded to include radio afterglows. After the 2004 flare, radio telescopes detected a faint expanding shell of gas around the magnetar. This was the nebula created by the material ejected during the flare. By measuring the expansion rate of this radio nebula, astronomers could calculate the total kinetic energy of the ejected matter. This confirmed that giant flares aren't just light shows, they involve the physical ejection of stellar material into the interstellar medium at nearly the speed of light. To truly grasp the energy release mechanisms, we have to look at the magnetic helicity. In a magnetar, the field isn't just a simple north-south dipole like a bar magnet. It is twisted. Think of it like a piece of rope that you keep twisting until it starts to form loops and knots. This helicity stores an enormous amount of energy. When a starquake happens, it's like cutting one of those knots. The field wants to untwist to reach a lower energy state. The energy released is proportional to the square of the magnetic field strength. Since a magnetar's field is 10 circumflex 15 Gauss and a regular pulsar's is 10 circumflex 12, the energy available in a magnetar is 1,000,000 times greater. This is why magnetars are so much more violent than their neutron star cousins. The crustal cracking itself is also an area of intense study. How does a material that is 1,000,000,000 times stronger than steel actually crack? Theoretical models suggest it might not be a single clean break like a glass vase. Instead, it might be a plastic deformation, followed by a series of microfractures. Some scientists believe that instead of one giant quake, there are millions of mini-quakes occurring all the time, which explain why magnetars are constantly humming with smaller X-ray bursts between their giant flares. The December 27, 2004 event was not just a landmark for astronomy. It was a wake-up call for planetary defense. When the wave of gamma radiation hit the Earth, it didn't just pass through. It slammed into the atmosphere with such force that the D layer of the ionosphere, the lowest part, which usually disappears at night, was suddenly and violently reionized. This created a massive VLF, very low frequency, radio disturbance. Navigational systems and long-range radio communications experienced a sudden phase shift. For a few milliseconds, the Earth's magnetic field actually compressed slightly under the pressure of the incoming photon flux. This was a galactic storm, a concept that had been theoretical until that very moment. It proved that the shield of our distance from the galactic center is not as impenetrable as we once thought. To understand the physics of starquakes at this scale, we must look at the breaking strain of the magnetar's crust. Recent simulations suggest that the iron lattice of a neutron star is the strongest material in the universe. Its breaking strain is approximately 0.1, which is incredibly high. For comparison, most earthly materials break at a strain of 0.01 or less. This means the crust can bend significantly before it snaps. But when it finally does fail, it fails globally. The crustal cracking isn't localized to a single fault line like the San Andreas on Earth. Instead, the entire lithosphere of the star undergoes a yield event. The magnetic field lines, which are undergirded by the superfluid mantle, act as a massive spring. When the crust yields, this spring recoils, and the resulting kinetic energy is converted into a magnetospheric fireball. This leads us to the energy release mechanisms involving photon splitting. In the intense magnetic field of a magnetar, 10 circumflex 14 to 10 circumflex 15 Gauss, the vacuum of space itself becomes polarized. In this extreme environment, a single high-energy gamma-ray photon can spontaneously split into 2 lower-energy photons. Conversely, 2 photons can merge into 1. This quantum electrodynamic QED effect acts as a sort of thermostat for the giant flare. It limits the peak energy of the photons that can escape the fireball, which is why we see a very specific cutoff in the energy spectrum of these events. The fireball is essentially a trapped soup of light and matter, held in a magnetic cage that is stronger than the internal pressure of the light itself. The observable effects across the electromagnetic spectrum also include a radio afterglow that persists for weeks or months. In the 2004 flare, the ejected material, amounting to about 10 circumflex, 22 grams of matter, roughly the mass of a large asteroid, expanded into the interstellar medium at roughly 70% the speed of light. As this shrapnel hit the surrounding gas, it created a shock wave that emitted synchrotron radiation. By tracking this expansion with radio interferometers, we were able to calculate the geometry of the explosion. It wasn't a perfect sphere. It was an oblate expansion, proving that the magnetic field directs the flow of matter even after it has been blasted off the star's surface. Let's revisit the 1998 and 2004 giant flares to see the pattern of recurrence. SGR 1900 plus 14, the source of the 1998 flare, showed significant pre-flare activity. For months leading up to the giant burst, it emitted hundreds of short bursts, small X-ray pops, lasting only milliseconds. These are the foreshocks of the starquake. Just as geologists look for small tremors before a major earthquake, astrophysicists now monitor magnetars for burst storms. If a magnetar starts chirping with small bursts, it is a sign that the magnetic tension is reaching a critical threshold and a giant flare might be imminent. The physics of starquakes is further complicated by the nuclear pasta phase at the base of the crust. As you go deeper into the star, the pressure becomes so great that nuclei are squeezed together into strange shapes. There is gnocchi, spherical blobs, spaghetti, long rods, and lasagna, flat sheets. This pasta is thought to be highly elastic and may actually dampen the seismic waves from a starquake. However, if the magnetic field penetrates deep into this pasta layer, the resulting magnetic elastic coupling could create even more complex oscillations. This is why the QPOs, quasi-periodic oscillations, detected in the tail of the 2004 flare were so exciting. They contained multiple frequencies, some of which were likely harmonics of the pasta layer vibrating. Finally, we must consider the magnetic reorganization that follows. A magnetar is like a wound-up clock. Every giant flare is a tick of that clock, releasing some of the stored magnetic energy. But as the energy is released, the star's rotation usually changes. In the 2004 event, the magnetar experienced a glitch, a sudden increase in its rotation rate. This happens because the starquake allows the faster rotating superfluid interior to couple with the slower rotating crust, transferring angular momentum. It is a violent, star-wide reset. This section has covered the sheer, terrifying power of the Magnetar's tectonic life, from the microscopic pasta at its core to the ionization of Earth's atmosphere thousands of light years away. A starquake is the ultimate testimony to the power of magnetism. It is a reminder that we live in a universe where even the stars can tremble, and when they do, the whole galaxy feels the vibration. Closing. As we look back at the journey we've taken, from the crushing depths of a Magnetar's iron crust to the echoes of radio bursts traveling across billions of light years, one thing becomes clear. The universe is far more vibrant and violent than our eyes can perceive. Magnetars are the ultimate testament to the hidden power of the cosmos. They remind us that magnetism, the same force that gently holds a photo to your refrigerator or guides a compass needle, can, under the right conditions, become a force that bends the very laws of physics, deforms the fabric of atoms, and lights up the entire electromagnetic spectrum. While these magnetic monsters may seem like distant, terrifying anomalies, they are a vital part of the celestial tapestry. They are the laboratories of the extreme, pushing the boundaries of what we know about matter, light, and the vacuum of space. Every starquake we detect, and every fast radio burst we trace back to its source, brings us one step closer to understanding the grand architecture of the universe. We live in a golden age of discovery, where the ghosts in our telescope data are finally revealing their faces, and the mysteries of the high-energy sky are beginning to yield their secrets. Thank you for joining me on this deep dive into the magnetic heart of the cosmos. Exploring these mysteries is a reminder of how small we are, yet how far our curiosity can reach. If you enjoyed this journey through the world of Magnetars and want to keep exploring the furthest reaches of space and the deepest secrets of science, please consider subscribing to The Science Pillow. Don't forget to hit the like button if you found this exploration as mind-bending as I did. It truly helps the channel grow and allows us to keep bringing these cosmic stories to life. Leave a comment below. What's the most terrifying fact you learned about Magnetars today? Is it the starquakes, or the fact that they could wipe your credit cards from the moon? I'd love to hear your thoughts. Until next time, keep looking up, stay curious, and remember, the universe is always more attractive than it seems.